Good morning, everyone. Today, we are in the second day of the Faculty Development Program on Emerging Topics in Applied Science 2025. We have a dignitaries, plenary speaker of the session, Mr. B.S. Dayananda. Also, we have conveners of the FDP, Dr. Suryanarayana K., Dr. Gopalakrishna Bhatt, and Dr. Anantakumar Kulakarni. Today's subject is chemistry, and the topic is electrospun nanomaterials and their applications. So in this regard, I, Amita H. from Physics Department, welcome you all on behalf of the Department of Basic Science, Srinivasa Institute of Technology, Valachil, Mangalore. We are gathered here to exchange knowledge and foster growth and testament to our shared passion for learning and professional development. So the subject electrospinning has emerged as a powerful technique for fabricating nanostructured materials with remarkable properties, making a significant impact in fields like drug delivery, energy storage, filtration, and optoelectronics. With advancements in material science, these nanomaterials are revolutionizing technology and healthcare, offering innovative solutions to real-world challenges. I'm sure today's session will provide us with valuable insights from experts in the field. It's my great pleasure to welcome all of you to this enlightening faculty development program. First and foremost, I extend a warm welcome to our distinguished speaker for today, Mr. B.S. Dayananda, a highly accomplished scholar and researcher in the field of chemistry. With a strong academic background, including an MSc and a PhD from Mangalore University. Mr. Dayananda's expertise spans organic and medicinal chemistry, structural chemistry, and photonic applications of nanocomposites. His remarkable research contributions include 10 Scopus and Web of Science cited publications, demonstrate his profound commitment to advancing science. His work in cutting-edge areas such as drug delivery systems, optoelectronic applications, and polymeric composites. In addition to his extensive research experience, Mr. Dayananda also has a notable career in teaching. With over 4 years of experience as a faculty member shaping the minds of young people. We are indeed fortunate to have such a versatile and dedicated expert with us today. Once again, I welcome you to this gathering. A warm and special welcome to all the online participants joining us from various institutions from all over Karnataka. Your enthusiasm for learning and active participation make this session even more enriching and meaningful. I also take this opportunity to extend a warm welcome to our conveners, coordinators, and all my dear colleagues. Your presence here reflects your commitment to enriching the academic ecosystem. As we embark on this session, let us actively participate, share ideas, and seek inspiration to apply these insights in our respective fields. Let us make the most of this gathering and create a vibrant platform for learning and collaboration. With that, let us welcome our speaker, Mr. B.S. Dayananda, to begin today's session. We look forward to learning from your knowledge and experiences. Thank you, and let's have a productive session ahead. Over to you, sir, Mr. Dayananda.
So thank you so much, ma'am, for the beautiful introduction. So I'm extremely happy that there are many teaching faculty interested in the topic. I'm delighted to be here to share my insights on the electrospun nanomaterials and their applications. To start, to start, I'll begin the today's session. So I'll be starting with the nanomaterials and some of the examples for nanomaterials and then properties of nanomaterials. And then I'll be moving to the main part, that is electrospinning technique. So under electrospinning technique, we will be discussing about different types of electrospinning techniques. And then most importantly, parameters that is governing the electrospinning process. And at the end, we'll be discussing about the, applications of electrospun nanomaterial that or electrospun nanofiber mat. So we'll be discussing about under the applications. Under application, we'll be discussing about the application of this nanofiber mat as a drug delivery patch, and then we'll be discussing about the application of this nanofiber mat as a wound dressing material, and in and after that battery applications of this nanofiber mat, and again the application of this nanofiber mat in the removal of toxicants from waste. And then we'll be studying about the OLED application of this nanofiber mat. So coming to the nanomaterial, you all know that the where the particle size is in between 1 to 100 nanometer. So in most of the cases we'll get the desired particle size. So the particle size will be in between 1 to 100 nanometer. In some of the cases we can also expect the particle size that is, but still it will be considered as, if it is less than 500 nanometer, it will be considered as a nanomaterial. So we all know that nanomaterial is different from our normal material. So they exhibit unique properties compared to its bulk material, correct? No, and it is known for its high surface area to volume ratio and its quantum, correct? No? So these materials can be engineered in various shapes and sizes through top down or bottom up synthesis method. So we have different synthetic strategies by which we can produce or we can prepare this nanomaterials. We have top down approach. In top down approach, we'll be starting with the bulk material, and then that will be converted into a nano size structure. And in case of bottom up synthesis, we'll be assembling atoms and molecules to form a nanostructure. So we all know that this field has already revolutionized in most of the fields. This has got several applications such as in medicine, in electronics, energy, in environmental applications, in environmental science. So these are all the some of the examples I have given here. So which are in nano sizes. So an atom is about zero point 0.3 nanometer in size, and if you look at the size of carbon atom, that is approximately 1.4 nano size. And see, this is the atomic structure where the linkage between two carbon atoms, that is to be 0.12 to 0.15 nanometer. And apart from this, we also have DNA helix. Okay, so this is DNA double helix structure, so which has the diameter of 2 nanometer. And then we have, see, the bacterium genus Myoplasm we have, so that has the length of 200 nanometer. See, this is RBC, that is red blood cell we have, that is its size is almost 6,000 nanometer. It is comparatively bigger myoplasm. And okay, and see, this is more relatable, and it is very much into whatever the human hair. If you look at the size of this hair, it is 80, more relatable. And you can see how if something has 100 nano, of human hair, how small it is. So it is that structure. So we'll be discussing more about such material today. To put this scale in a context, see the size to a meter is the size of the earth. So now you can imagine, if we consider any nanomaterial, correct, no? So moving to the properties of nanomaterials, we all are familiar with the properties of this nanomaterials. So this, once you reduce the particle size to the nanoscale, what exactly happens is, see, electron distribution will be changed. So what happens is, like, this electrons will be confined in a space. So once it is confined in a space, so it will exhibit totally different properties from the bulk material. See, suppose if you have opaque substance, see, if I take copper as a bulk material, it is opaque in nature. But the material, if you convert to a nanostructure, and materials will be stable, once you convert them to a nanoform, that will be highly combustible. And this is true in case of aluminum. The bulk material, non-combustible, it is not that much combustible. But once you reduce the particle size to nanoscale, it will be highly combustible. And see, in the insulator become conductors. Okay, so suppose if you have some bulk material, it is insulator in nature. But if you convert them nano size structure, so that can be conductive in nature. Because when you change the electron distribution, see this what happens is, like, when you reduce the particle size, the energy gap, that is the energy between conduction band and valence band, that will be reduced. So that is why insulator can turn out to be conductor when you reduce the particle size to nanoscale. And in certain cases, the solids turn out to be liquid at room temperature. And these nanoparticles, they tend to be more chemically reactive than their ordinary size parts, because they have more surface area, correct, no? So as we all know that this nano material is known for high surface area to, so chemically they are more reactive, correct? So that is why in most of the chemical reactions we use nano catalysts, because they provide the surface area for reaction to take place. So that will provide the large surface area upon which these chemicals can react. Okay, and so at the same time, an increase in surface area to volume ratio alters materials mechanical, thermal, and catalytical properties. And in today's session, we'll be focusing more on the electrospinning technique. So this is one of the techniques. So this will be listed under top-down approach. I told you. So we can synthesize nanomaterials either by top-down approach, or we can prepare bottom up approach. So this electrospinning technique, it will come, it will be considered under top down approach. So it is a technique, one of the nanomaterial. So here, whatever the nanomaterial we will get, so that will be in the form of nanofiber. Clear? See, from the word electro, it is very clear that, see, there is a electro. So we need some electricity, and in the presence of electricity, so there will be a spinning. So that is what from the name we will understand. So it is electro spinning, correct? So it is a simple and comprehensive process generating an ultra fiber from materials which include polymer, composite, and ceramic. Okay, so by using or by making it with the other material, by adding certain additives, we can make the nanofiber. Okay, so we have to prepare the we have to add certain additives, then we have to subject them for the electrospinning process in the presence of very high electric field. So recently, if you look at the literatures, you get plenty of research articles that is coming up with this electrospinning technique. This solving based on the unique properties. So just like any other nanomaterial, so even this nanofiber also has got a very high surface to volume ratio. At the same time, this also offers so many other advantageous properties. So it has got high tensile strength, large surface area, and porosity. And see, what do you mean by electrospun nanofiber? So it is simple. So it is a nanomaterial that is obtained from electrospinning technique. See, so this is a human hair. What is there? It is of nano. So whatever the small thin structures, whatever we can see down this human hair, so that they are all nanofiber. Now you can compare here is how big it is in front of nanofibers. So this is a SEM images that is recorded by keeping human hair placed on a mat. So the smallest nanofibers made today are between 1.5 to 1.75 nanometers. See, so once you reduce the particle size or the nanofiber to less than 600 nanometers, generally we cannot see the nanofibers. It is very difficult to see with the naked eye. So we have to go with a certain advanced, instrumentation techniques. Okay, see, whatever the image I have attached here, attached here. So this is a nanofiber mat. So that is fabricated from electrospinning technique. Here individual nanofibers we cannot see, just because whatever the diameter of each individual nanofiber is less than 600 nanometer. So that is why we have to use some advanced techniques to see. Okay, so under SEM tech, how we see this nanofiber mat. So this is an individual nanofiber mat. So that is, see this nanofiber mat under or the scanning electron microscope. So it will look like this. Okay, and see, we all have come across the drag line. So in spider drag line, normally we can see the fiber. So its fiber is 3000 nanometers. That is why we can see with the naked eye. And coming to the spinning setup, we have two setups. One is vertical setup, and one is vertical setup. Okay, very simple. In case for vertical setup, the spraying is done from the top. The spraying is done vertically. See here in the image, you can see the spraying is done from the top. And in case of horizontal setup, here the pump as well as the collector, so that is kept horizontally, and even the spraying also it is done horizontally. Okay, see, these are some of the components. See the main components of electrospinning it. See, we have high voltage power supply. So otherwise we cannot spin it. See, we have high voltage power supply. So generally the voltage will be in between 5 to 50 kilovolts. So we'll be dealing with that much high voltage. So we should be extremely careful, because we'll be with see 5 to 50 kilovolts. Okay, we are not dealing with the volts, it is kilovolts. And next one, spinner. Spinner is the need of the voltage power, and then we have the syringe that you can see here, and to that we have connected the needle. So that is as a spinneret. And in the syringe, whatever the syringe we can see here, there we have to fill the whatever the polymer solution we prepare, so that we have to take it in the syringe. Okay, and then we have grounded collecting plate. So then we have the collector during electro spinning process, we get the nanofibers, right? So that will be collected on the surface of the collector. Okay, so we do have different types of collector, usually metal screen plate or rotating mandrel could be used as a collector. So these are spinning setup, and apart from that we do have setups. We have to give the, see, once we use this rotating mandrel or screen play rotating mandrel, you have to give the rotate. Okay, and then the flow rate also you have to set the rate at which the polymer solution is pumping out of this syringe. That has to be fixed in the beginning itself. So that has to be optimized in the beginning itself. See, this is technique. So here now we will get more clarity about electrospinning, what it is. See, here, this if I take, so this is, I told, so we have vertical setup as well as horizontal setup. And so this is a vertical setup where the spraying is done horizontally. Correct? Now see here, we have the syringe like structure where to fill the, we have to take the polymer solution, and then it is connected to the spinneret. So generally, the metallic needle will be used as a spinneret. See, the spinneret, the polymer solution is coming out. See how it is spraying. So this is, coming and vertical setup, and this is also vertical is little bit modified, and this is moving, so it is continuously moving. So certain modifications that can be done, and this is a whole one. So this is a collector. I told, the collector, either it could be rotating drum in some cases, based on our application. Like this collector also, instead of drum collector, we can also keep the vertical plate. Okay, see, this is a drum collector. If you use the collector, the rotation per minute for this drum, that has to be fixed in the beginning itself. And apart from that, flow rate also has to be fixed. So starting the electrospinning, we have to set certain things. So that while setting the different parameters, we have to set the polymer solution, set the rotation per minute for the mandrel. That is when you are using this collector spinning technique, where we are not using. So this is, it is coming under still less electrospinning. So here we are not using needle. It is needle based electrospinning technique. Okay, see here, the spraying rate is more, and the amount of nanofiber mat whatever we get after the process more in this case. This has got some edges over this single fluid electrospinning technique. See here, you see it. See, when it is about to spray, so it is taking a conical shape. It is a tailor cone. So that is very much important. It is very crucial in the electrospinning process. The formation of proper that decides the morphology of the nanofiber mat to be formed. Clear? So this is how the electros process is done. And coming to the mechanism, how exactly the nanofiber mat is forming out of this polymer solution. Given here, see, I told you we have to take the polymer, you have to prepare the polymer solution, and then we have to take it in the syringe. Then the needle, the spinner or the needle has to be connected. So as the voltage is applied, what happens as the voltage whatever the solution we have at the tip of the needle, that gets charged. Correct? In the presence of electric field, the polymer solution we have, that gets charged here in the presence of electric field. Due to, there will be a repulsive force between like charges. So there will be a repulsive force between like charges, which causes the polymer that will be deformed into a cone-like structure. That is what we have seen in the previous case. See, this will be pushed out, and that will take a cone-like structure. So at a threshold voltage or at a critical voltage, what happens? So the repulsive force I told, that repulsive force that comes the surface tension of the solution. So for each polymer solution, so there will be a surface tension. So when we take polymer and along we do add certain additives, right? So because of that, surface tension also. So at the critical voltage, what happens is the repulsive force that will overcome the surface tension, and this polymer jet will that from the spinneret, and then it will be towards the collector. Then it will be drawn towards the collector, that is due to the electrostatic attraction. If this is positively charged, this is negatively charged. So there will always be a attraction, right? So because of that will move towards, it will be drawn towards collector, and the nanofiber gradually it will be collected over the on the. So this is the simple mechanism of this electrospinning. And See, I told you, under electrospinning technique, we have mainly two types. One is needle-based electrospinning, another one is needleless electrospinning. And this needle-based electrospinning, that is most commonly used technique. Okay, and use needle to deliver the solution. Correct? No, so we prepare the polymer solution and then we fix the needle. Okay, so you needle to deliver the polymer solution. So under this needle-based electrospinning technique, we have three more types. Okay, so we have single electrospinning. We also have so that I have not listed here. So in case of single phase electrospinning technique, the fibers are composed of only one structure, be composed of material or a blend of material with the bioactive substance. Okay, so in case of a single phase electro, so add the solution, and if you need some other polymer to be mixed, that also we will add, and then we'll add a little amount of additives, and then all together we take a and we fill it in the needle, and then we load for the electrospinning. So that is why it is single phase electrospinning. Clear? In case of coaxial electrospinning, or it is also known as core sheath electrospinning, and this in case of coaxial electrospinning, it is clear that there is a core component and there is a sheath component. So here it is similar to this single phase electrospinning. Whatever the spinner that we have, so it's modified. So there is a provision to fill two separate solutions. See, the core component can be taken in middle of the needle, and then the sheath layer can be filled peripheral. Okay, so the here it is just similar to single phase electrospinning technique, but the spinneret is modified. Okay, and see, this is most when we are when the intended application is it is for intended for biomedical applications. In most of the biomedical applications, whatever the drug we gonna load, that will be that may not be that stable, that has to be prevented from the interaction with the outer environment. In that case, the drug has to be taken as a, and then it has to be covered with the sheath component, and most of the cases we use polymer or mixture of polymers we use as a. And apart from that, we also have multiple spinning, so where we have several spinneret. Okay, we have multiple spinneret that will be sprayed simultaneously. And apart from that, we also have melt electrospinning. Say certain poly not soluble in any of the solvents, whether you try with water or whether you try with organic solvents, they are not soluble. In that case, to spin such solution, we have to go with the melt electrospinning technique. That means we have to perform the same process condition. So we have to use. And second one, we have needleless electrospinning also, and here it is also known as nozzle free electrospinning. And see, it uses a rotating drum or a liquid surface as a emitter. So here having a needle polymer solution. Instead of that, so we have a collector drum, it rotating drum. So we have to take the solution in the rotating drum. So the surface of this rotating in such a way that this has got n number of pores. Okay, n number of pores, and through that pore subsequently that will be collected. So again we have different types of rotating drum, or we also can use a drum. Clear? So see, this is a ball spinneret and this is a cylindrical spinneret, and we have spinal coil spinneret, and we have different types of spinneret here. Okay, and it is we are not using a needle, that's all. So that is the only difference. And here high throughput can wide range of diameters. And see, this is a this is the aluminum foil where we have collected the nanofiber mat. So after the electrospinning process, we get this kind of structure. So this is like a nanofiber mat that can be peeled off. That can be, and the nanofiber mat also could be modulated. And so this is some image of single phase and coaxial electrospinning. So single phase the nanofiber mats that is obtained from single phase electrospinning. It is a simple one. It will complicated structure, but some image of the nanofiber mat that is obtained out of coaxial electrospinning technique. So you can see we have hollow structure here, so that will have can have different components. So based on the type of the materials we have taken as a core component, and the morphology of the nanofiber mat also will vary. So here you can see the as a core component we have one substance, another component. Okay, so that is very much interesting. And now, so to start the electrospinning, so the first material we are going to use is it is a polymer, correct? No, so under polymer we have different types. We have synthetic polymers, have synthetic polymers, and we have composites. Okay, so either you can make composite, we can use a natural polymer, or we can use a polymer. So under have different types, correct? No, so we all know that we have collagen, collagen, chitosan, gelatin, protein, fibrin. We have large number of natural polymers. So this is used when the nanofiber mat is to be used for a biomedical application. To have so this natural polymers, they are known for their biocompatibility and less toxic. The nanofiber mats to be the so it is always said with the animals. And also this then see most of the natural polymers, they have some intrinsic be like adhesive. Okay, so that is very much advantageous to be used in the biomedical application. And on also have synthetic polymers that also offer many advantages over natural polymers, as they can be tailored to give a wide range of properties and mechanical property and degradation. So, polymer also could be used to pair the nanofiber mat, and the property of this synthetic polymer also it could be tailored to a different type of PLA, that is polylactic acid. We have polycaprolactam, polyurethane, and polypropylene, polyethylene. We have nylon, udrigit. We have several synthetic polymers. Okay, so the this is the first choice. So whenever you want to start choice is polymer, so that we have to fix. So once you start decide the polymer, the next step is to select the solvent. So important. So we have to select the solvent very carefully, because whenever we choose the solvent to dissolve the polymer completely, so that is very much mandatory here. Because see, even if you have small particle in the, and if it is not soluble completely, or if it is sparingly soluble during the dissolution process, can happen. You can imagine you have electrospinning setup where we have the needle and it is connected to the syringe, correct? So the needle this diameter will be very very small, so even the smallest particle can also block the electrospinning. So that is whenever we choose the completely. So that is the first to select the solvent. And also in the integrity of the polymer during that is very much important. That means, so whenever you dissolve the polymer, not change the structure of the polymer, so the integrity of the polymer should be retained as such. So that also should be taken care. And also it has to carry the dissolving molecule towards the collector. Okay, so once you dissolve the polymer in the solvent, so during spinning process, it able polymer molecules towards the correct collector. Okay, so this factor the solvent vapor polarity. See, in most of cases extreme in a solvent can, because see, suppose if you use acetone, that also certain modification you have to mix with the solvent. And when you choose the, since it is highly we all know that before spraying as the electric fog that so coming out from the needle, immediately it will solidify, so it will not reach a collector. So once it solidifies the tip of the needle, what again the spraying is not possible. Like the we have to be extremely careful, extremely high solvent use. Even if you select see, sometimes with other option, because it will be soluble only acetone, and in that we have to use certain other solvent, like DMF, high boiling solvents to be used, and to overcome the spraying. Yeah. And viscosity and surface tension also influence the fiber morphology and size. And see, these are some of the choices that is to take solvent. So see, we have that is polyvinyl alcohol. So we are all familiar with ketone and all. So if you want to make a electron mat of you have dissolve it in water. Okay? So we have to take it in a water and to be used. But in most of the cases, the chitosan is very difficult, because see, even if you chitosan solution, the viscosity will be very high. So you might have encountered the same problem. So if you prepare % chitosan solution, this solution not come out from the needle itself. It is that thick. So these are the polymers and its solvent. Okay. So the selection of solvent, that plays very important role here. And then these solvents. So this is especially the surface tension has to be taken care, because surface has a major role in the electrospinning, or which can decide the morphology of the nanofiber matter. And generally the solvent with the low surface tension, that is preferred over high surface tension. See some of the solvents tension is we have to consider. And this will be moving to the next topic. This is very important. So the parts which can ultimately like the morphology of the nanofiber. So it is divided into three types. And it is divided into three types. One is solution parameter, and then process parameters we have, and then ambient parameters. So under solution parameter, we have molecular weight, viscosity, surface tension, conductivity. These are the parameters to be taken care when we prepare the polymer solution for electrospinning. And this is a process parameter. So this has to be taken care when we operate the process. This is ambient parameter, that is temperature and humidity. So go through the parameter one by one. So first one, concentration. See, whenever we choose any solvent, any polymer, the concentration is very important. See, the given polymer cannot electrospin concentration. See, for example, PVA will be electrospinable. It is properly electrospinable at 10%. 10% of PVA can electrospin properly. And if you increase the concentration, if you also can be electrospin, but it will be very difficult, and the fiber more. Okay, so here this is the same image of the nanofiber mat. So this is the nanofiber mat. So where we have the optimum concentration for the electro spinning technique. So whatever the nanofiber we got here, so that is smooth, okay, beadless morphology, we can say. In other side, see, we have this is a beaded like structure. This happened, that is mainly so that was not proper, that not proper. And here, see, it has been found that the low solution concentration, a mixture of beads and fiber is obtained. And if you take if the concentration is very less, to get the proper structural morphology, surface go is the optimum concentration. And with different molecules. If I consider chitosan will come with the low molecular weight, medium molecular weight, high molecular weight. So see, the molecular weight affects the morphology of electrospun nanofiber, and high molecular weight polymer solution have been used in electrospinning the desired viscosity for the fiber generation. Molecular weight polymer will be preferred because that can provide the required viscosity for the fiber generation. It has been that two low molecular weight solution tend to form beads rather than fibers, and high molecular weight solution gives average diameter. See, fiber diameter. This is some images of nanofiber mat where we can see the bead formation. Whatever the molecular weight we have taken, so that was it was not suitable for the proper electrospinning process. Okay, and next one is the viscosity, and viscosity also decide the morphology. And here the viscosity is very the polymer solution. Inject polymer solution from the through the needle will be extremely difficult. So solution will be that thick, and I found that the very low viscosity there is no continuous fiber formation. So you can get the fiber formation, but it will not be continuous. So while preparing the solution, the viscosity also has to be optimized properly. And next one is the surface tension. So will explain the mechanism itself. Surface tension has the major role to decide the fate of the nanofiber matter. Generally, high surface tension of solution inhibits electrospinning process. So if you use so if the surface is very high, so that can inhibit the electrospinning process. So the formation of droplets, beads, and fibers depends on the surface tension of the solution, and a lower spinning solution helps electrospinning to occur at a low electric field. So that means it is always preferable to go with the lower surface tension, because which can be electrospun at a lower electric field. Okay, so that's why whenever we choose we have to look into its surface tension. And next one is the conductivity. See, in order to spin, the solution need to have conductivity. So then only we can use for the spinning. And the solution conductivity is made by polymer type, solvent used, and the availability of ionizable salt. So it has been found that the increase of the solution, so there is a significant decrease in the diameter of the electrospun nanometer. The low conductivity of in insufficient jet. Suppose the conductivity is very less, then the elongation of the jet during the process is extremely difficult. Generally, electrospun nanofiber fiber that obtained with the highest electrical conductivity. Whatever the nanofiber we get for the nanofiber, so that will be very less. And suppose the conductivity of the polymer solution, that could be tuned, or that could be modulated. If it is not conducting, we can add certain ionic salts, and we can modify the conductivity. So such as sodium chloride salts can be used to increase the conductivity of the polymer solution. And coming to the voltage, so it's an important parameter. It's a crucial element in the electrospinning process. Only after attainment of threshold voltage, the fiber formation occurs. Clear? See, the fiber formation takes place only after the attainment of it. So polymer solution, the threshold voltage is different. So that has to be optimized for that. The particular at a particular voltage. So once you optimize the voltage, easily you can electrospin. Okay. In most cases, high voltage causes us due to the force in the channel. It the operation solvent from the polymer jet. To increase the voltage, so the operation rate of the so that will also be more. Correct? See, during electrospinning technique, I told you. So when you solution in the presence of electric field, the polymer solution will come out from the jet, and during its travel from the needle tip to the collector. So the whatever is used, that will evaporate, reaching the collector. That will be, and only polymer and whatever we have added during the preparation at the format. So that the selection of solvent also it is very crucial, and the applied voltage it is very at voltage there is also greater. If you keep the voltage very high, and whatever fiber morphology we get, so that will completely different. So here you can see the like bead like structure. So this there we will get use the voltage in very high voltage. Then the flow rate. See, in most of the cases, the keep that's for PVS solution though we just 0.5 to 0.8 ml per hour. So in one you can 5 to point PVS solution. Then see to get one nanofiber mat, you minimum you need hours. Spraying only 1 per hour. You imagine how thick nanofiber mat we can it depends on the nature of the what some cases for you use 1 ml 2 ml of the nanofiber mat we receive or get at the end, so that will be more, and this has to be beginning itself. Okay, so influence the jet velocity and the material transfer rate. A lower feed rate is more desirable, correct? So that is what I told. So generally we keep very lower feed, and it is desirable as a solvent will get enough time for evaporation rate, correct? No? So this if you keep the flow rate very high, so the solvent along with this polymer solution we can say, so that will not get sufficient time to be evaporated. So to get proper nanofiber mat, so the flow rate has to be fixed. I mean the flow rate has to be, so it results in fiber proper tip to collector distance also we have to fix in the beginning itself. So generally we keep 10 to 15 centimeter distance we maintain from the tip collector. Okay, so it has been found distance is required to give fibers sufficient time to dry before reaching. Otherwise, either too close or too far, beads have been observed. Okay, so some distance has to be, if the distance is too far or too close, bead formation will be result. So it has been reported that the flatter fibers can be at closer distance, but with increase in distance, rounded fibers have been observed. And then the collector told earlier. So in most of the cases, aluminum foil will be used as a collector. So that will be covered on the mandrel. Aluminum foil will be used as a another collector also can be used based on our we can have paper, conductive cloth, and mesh, etc. And last one is temperature. So it is very important. So using high boiling solvents, sometimes we may need to use little higher temperature. Otherwise, it will not be evaporated completely the nanofiber mat. It could be to the increase the temperature, known polymer solution will be reduced. So because that finally influence the morphology of the nanofiber mat. So this is this one I have what happens to the when you play with the different parameters. Once you prepare the nanofiber mat, so we have to characterize them, correct? No, so we have to characterize them by using several analytical and spectroscopic techniques. So it is very important because we'll be dealing with very high electric field, and whatever the additives we add, so they become at wage. And sometimes the integrity I told, so it is always we have to be taken care of the polymer solution. It should not be disturbed, correct? No, so to check whether the polymer is in the polymer is intact, or whether is there any structural modification for the polymer after electrospinning. That also has to be. To do that, we have to go with certain characteristic technique. So the SEM, that is a field emission scanning electron microscopy, that is we call, so that will be used where we check the morphology of the nanofiber mat. We'll get to know the diameter of nanofiber mat by using analysis. SRD, PXRD analysis, that will be used to check the mat. So the crystalline nature of the nanofiber mat, it will change more. So that can be monitored by using PXRD analysis. And then also very important, so here under mechanical properties, we about tensile strength and Young modulus, strain at break, elongation at many properties under this mechanical properties. And then we have thermogravimetric analysis, that is TGA. So to know the thermal stability of the nanofiber mat, we use this TGA technique, and then the FTIR. So to establish the interaction of the drug, suppose if you add in the preparation drug and the polymer, to establish the interaction between these two, that can be used, or also can give the idea of the certain functional group present in the polymer. And so this is implication based, like UV spectroscopy can be used, suppose if the mat is intended for fluorescent application, and the cytotoxic can be used if it is intended for biomedical application. Apart from that, so based on our application, the different characteristics could be utilized or could be employed. Coming to the application of this electrospun nanomaterial, so we all know that once we synthesize or prepare the electrospun nanofiber mat, so because of its unique properties such as area, high tensile strength, it has got several applications. So you can say application as scaffolds, sensors, filters, membranes, battery material, catalytics. Everywhere we use this, you can use this electrospun nanofiber mat. So we'll discuss one by one. So first one is drug delivery. So in this, under this, we'll be, we'll be choosing the right drug, and we'll be incorporating polymer solution. And we have to go flip. So whatever the nanofiber mat we get, so finally you will have the nanofiber mat which will be loaded with the drug molecule. And why we have to load the fiber mat? Because this nanofiber mat, whatever we have fabricated, that has got several advantageous properties. Correct? No, it is a materials have emerged as a promising platform for a drug due to their unique properties and versatility. High surface area to volume ratio enhances the drug and the surrounding environment. See, it allows for the design of drug delivery system with the tailored release profile ranging from immediate release to this. Okay, see, if you want to achieve the sustained release, we can modify the electrospinning technique. So we can go with incorporate this biomaterial or drug component as a core component, and the subsequent release from the nanofiber mat will be very slow. That can finally we can attain the sustained and slow release. And see, it can accommodate wide range of drugs. Under so we need a hydrophobic drug, and we have hydrophilic drug. All type of drugs could be incorporated in the nanofiber mat. And then the bioavailability. So for this, we have to select the polymer wisely, and choose the polymer. We have to select the polymer in such a way that that has to be biocompatible and should be biodegradable. So inside body, it has to be biocompatible, and it has to degrade without leaving toxic byproducts. And then the protection of now that will really unstable, that can oxidize if you keep it open. In that case, we have to go with the coaxial electrospinning tech, where we can load as a co-component, can protect outer environment. So here one of my work, so that was published in Chemistry Select. So here initially we had synthesized series of 2 hydroxy flavones, so 3-hydroxyflavones, and all the size compounds rated for antioxidant, anti-inflammatory activities. And this compound, that is dimethoxy derivative compound, and its cytotoxicity was initially assessed. So it was found that the compound was almost non-toxic up to 50 microgram per ml. And then it was evaluated for wound scratching assay. So from wound scratching assay, one will understand wound healing ability of the compound. See what happens whenever you have any wound in your body. So the body has got self defense, got a natural healing ability. So if you create any hole, so the normal cell will try to migrate towards the heel, that is a natural mechanism that is taking place in our body. So with the incorporation of this compound, it was found that the healing was found to be improved by incorporating this compound. So then it was decided no the drug delivery of this through electrospun nanofiber mat. So that is why it was, since it was a good anti-inflammatory agent, it was less toxic, and at the same time it was having a very good wound healing property. So that is why it was decided to load into the nanofiber mat. So here for loading this one, so this was intended for as material actually. So the cellulose acetate was taken as a polymer here, and then solvent system, whatever we acetone and DMF, rate was fixed at 0.5 ml per hour, and then voltage was fixed at 9.6 kilovolt, and the working distance centimeter. Okay, and this is the image of pristine nanofiber. That means it is the nanofiber mat that is created using just cellulose acetate. So that is known as pristine nanofiber. And B1, so this one is compound loaded nanofiber mat. And it was characterized by some analysis. It was found that, see, this first one is the neat nanofiber mat, so without so it was found that the fiber diameter was reduced from 114 nanometer to 80 nanometer. So upon incorporation drug or the compound in the nanofiber mat, it was found that the diameter of the nanofiber mat was decreased. That could be due to the improved crystallinity of the nanofiber. See, this is that reflected in the powder XRD. So first, whichever is there in red color, so this is the PXRD of profile of compound, synthesized compound, or the loaded. It was highly crystalline in nature, but upon incorporating into the nanofiber mat, the crystalline nature of the nano compound was reduced, but it was found to be more crystalline or more semi-crystalline than the neat cellulose state nanofiber mat. Okay, and also one could see that there is a shifting of characteristic peak of the cellulose acetate. Here in this case, it is shifted towards lower 2 theta value. And this analysis from TGS, it was found upon the nanofiber of the nanofiber mat was improved. I mean, it was enhanced. Here, to know the functional group present in the polymer as well as in the drug load. Since the loaded was very less, so only 5% of the loaded in the nanofiber mat. So that of the peaks corresponding to the compound that cannot be seen here. So only one could be observed 1649. So that could be due to that could be corresponding to CO functional group. And so this will interact between compound and cellulose acetate. So see, once you load into the nanofiber mat, so you have polymer and then you have so solvent will be operated in the process. Finally, whatever the nanofiber mat we get, so that in that you will have cellulose fiber and you have our molecule. Correct. No? So it was anticipated that there is a hydrogen bonding interaction between the load with the cellulose acetate. And mechanical property also it was analyzed. It was found that operating mechanical property also it was increased, and elongation at break it is decreased. That is mainly due to the improvement in the crystalline nature And see, this is more interesting. See, the anti-inflammatory activity of the compound at 200 microgram per ml, it was just 40%, I mean 40%, plus or minus 3%. But upon incorporating in the nanofiber, it found the anti-inflammatory activity of the compound also it was enhanced, or it is improved. That could due to the due to have nanofiber there, so that is why that has enhanced its anti-inflammatory activity also. And so it is always um, you know it is very important evaluation method. So whenever the drug, the nanofibrability has to be checked, because see, if you are using this nanofiber mat as a wound healing material, so that with the body fluid, correct? No, so it has to have some level of blood compatibility. This nanofiber mat was hemolysis, but the composite nanofiber, after loading the compound, the hemolysis percentage hemolysis was just it was higher than Stein cellulose acetate nanofiber mat. That is, it was just 6.29 nanometer. And see, nanofiber it could be acceptable. So it is considered as biocompatible if the percentage hemolysis, if it is less than 5%, considered as biocompatible. And again, we have also calculated the drug encapsulation efficiency also. So the drug efficiency was 82%. So this was a formula to calculate that. And see, in vitro drug release study also, it was in mat. So it was found that the drug was released from the nanofiber mat. See, whenever we load the in vivo drug release study, so whatever the drug we loaded, we have to make sure that it is if it is nanofiber mat, so that is of no use, correct? The importance to study the drug release studies, and drug release study was drug release study was conducted, and it was from that study it was found that it was the Zoda as well as Osmer-Peppas model, and it found that the drug was released in two stages. Okay, so in the beginning, one could find rapid release of 37%, and after that, in the second stage, there was a slow and steady release. So that see, altogether 91% of the loaded drug was released 3 hours pH and 0.2. So initially release was observed, and then slow release was observed. And see, this is another fiber mat for indication, that is periodontal intrapocket drug release study was conducted. So here we have used Udrejit as a nanofiber mat and eugenol. So we all know that this eugenol is known anti-inflammatory. So that, and it was delivery studies here also it was loaded, and here 4 different nanofiber mats were prepared by loading different concentration of eugenol. And here also nanofiber morphology was is different for different nanofiber mat. So diameter of the nanofiber mat will change from one nanofiber mat to another nanofiber mat, because whatever the drug we take here, so that loading eugenol. In second case, 1% eugenol will be loaded. Eugenol was loaded. Next one, 2% eugenol was loaded, and 3% eugenol was loaded. So the that is why the nanofiber diameter also it was different for different nanofiber mat. So see that branched structure here. So there is no bead formation. With that, we can say that the condition was properly optimized. We have the proper which is required for our application. And again, the water contact and it was swelling study was done. So once we fabricate the nanofiber mat, so if you put it in a water, it has to absorb the water. So that property must be there for the material, correct? So if it is intended for drug delivery application or for a wound healing application, if we are using it as a wound dressing material, water absorbing property should be there. So that also it was studied. And see, cell viability, cytotoxicity also it was cytotoxicity assay also it was evaluated. So from the toxicity assay, so by using NH3T3 cell line, it was evaluated. So it was found that the cell viability was more than 80%. That means almost non-toxic. And by using Drosophil also, the cytotoxicity was evaluated. So it was found that 80% of the had ability to survive. Okay, so that means whatever the nanofiber mat and the compound loaded or the drug Ejina loaded nanofiber mat, it was not toxic. And protein denaturation assay also it was evaluated. From here it was found that the reverse concentration dependent anti-inflammatory activity was observed. That means the nanofiber mat with the lowest percentage of Ejinal showed highest activity. So that is common in most of the natural drug release also it was studied. And here the encapsulation efficiency of the nanofiber 84% and 94. That means we have, since we had fabricated 4 different nanofiber mats, so the encapsulation it is different, and that is cumulative drug release also it is different from the different nanofiber mat. And from the, again, it was fit with the various kinetic model. It was found that it was well fit with the Cosmer model. And see the diffusional it was found to 0.34, 0.25. So that suggested that the it is the the release of drug or loaded compound from the mat through diffusion process. See? So whenever you use it for your real application, what happens? Either the loaded drug can and it can come out through the network, correct? No, so it was found that this the value of n, so that will give the idea how it has come out from the nanofiber mat. So whether it is diffusion method or whether it is surface erosion method. So the absence of cracks in the surface depicting that the predicted mechanism is Fickian diffusion rather than surface erosion. Okay, so similarly, audible. So see, similarly, let's go for this application. So we can take different polymers and we can load different study drug delivery studies. And coming to the next application, that is wound dressing material. See, whenever we use any wound dress, so this it has to meet certain criteria. So whatever the material we use for wound healing application, it has to avoid bacterial barrier. So if you plaster, it should avoid bacterial infection. Suppose if you have a open wound, what happens? It is a natural tendency that many bacteria can come and infect there. Correct? Again, the infection will spread. So whatever the wound dressing material we use, so if as property, that's well and good. And apart from that, that adequate gas exchangeability should be there. Whatever the dressing material, so that should have gaseous and it also provide moist environment and good drug delivery system. And to application of this electrospun nanofiber mat, I have discussed, I have included one work here, so where I have used see, I told they have, see, as a taken cyclodex complex, and along with the cyclodextrin they have used curcumin. So curcumin, it is active ingredient that is present in turmeric, so that antioxidant, anti-inflammatory, and so many other medicinal properties. So here the cyclodextrin curcumin was made cyclodextrin, and that was incorporated as a core component, and as a shell sheath layer or the shell layer with the mixed with the polycaprolactam, and again Asia corticoside, that is Asia ticoside, that was used. So that is the oxidant which can also support or which can enhance the collagen synthesis in the body. So that is why it is used here. See, this is the structure of Asia side, which stimulates collagen synthesis, deposition, and promoting tissue repair. So that is very much important. So collagen is very important for the core shell structure and clatheret configuration, what ensured sustained release of curcumin. So that is why, see, since it was the co-component, so it showed sustained release, okay, providing the desired antibacterial and anti-inflammatory function of the wound. And this was another work. So here also the core coaxial electrospinning strategy was used. Here the fibers are loaded with rifampicin, so and it is coated with silver nanoparticles. So rifampicin is it is a known antibiotic, and it is particularly it is effective, which will inhibit gram-positive bacteria. So this release rifampicin and silver at a synergetic antibacterial effect, stable over time and compatible substance. See, this was another nanofiber mat. So I had fabricated this nanofiber mat. So here we had strategized structure. So initially we have used base material. So material, and then we have taken Udregit has taken PV as a base material. As upper layer, we have taken Udregit. In the we have operated bacteriophage. So this work from it was published from so the fabrication part I have done, and it was evaluated for diabetic wound healing. So it is it was noteworthy that so whatever the fabricated nanofiber mat, it was showing improved efficiency or wound healing ability, uh, existing work. So see here the last one whatever is there, so that was the nanofiber mat. So where we had in the beginning first layer, we had second layer Udregit. So Udregit was loaded with the bacteriophage. Two bacteriophages we had loaded. So it showed a good wound healing ability. Okay, it is showed superior wound healing ability than the existing one. And similarly, here also we have so much scope. We can load different. We can choose volume and load drug candidate, and we can study as a wound dressing material. And in the dye-sensitized solar cell, know that in dye-sensitized solar cell, we have photoanode, we have electrolyte, and we have cathode. Correct? No? So the general that is involved in the conventional DSC is that so the low ionic conductivity, higher internal. We do have certain issues that electrospun nanofiber mat. So the incorporation of metallic compounds into nanofibers is advantageously employed in the electrospinning technique, owing to their conductivity and optic polyvinylidene. Polyvinyl pyrrolidine is most commonly used polymer matrix here, and titanium is the most widely used semiconductor. However, compounds such as tin, zinc, nickel have also been studied for the production of electrospun. See, when we talk about the sensitized solar cell, we have three places where we can use our electrospun nanomaterial. So surface of the photoanode could be modified with the nanofiber mat, or whatever the electrolyte we have, so that can be modified with the electrofiber mat. Apart from that, we also have a separator here which will prevent the short circuit. So that also could be modified with the electrospun nanofiber mat. See here, this is work that was published in the journal. So where the photoanode that was modified by electrospun titanium nanofibers and the conventional particles. So they have taken titanium dioxide initially, and then the surface of the titanium dioxide, it will be electrospun with the nanofibers, and then it was loaded with titanium dioxide nano particles. Okay, and it showed improved light harvesting, demonstrated 44% higher device efficiency than those made from just titanium dioxide nanoparticles alone. nano material, its efficiency is more. So over technique. This is another work to modify the electrolyte. So where they have modified the electrolyte, so they made nanofiber mat, but it's a fluoropropylene, that is PVDF, HFP. They have used and they have prepared the nanofiber as a electrolyte here. So they have made the nanofiber mat, and then the a few drops was adsorbed the surface nanofiber mat, and then it is made to contact with the photoanode. So this nanofiber gel electrolyte based cells exhibited better stability and maintaining 85% of efficiency after 150 hours. And so this is another work, similar work, but here also modulated. It was modified with the nanofiber mat. So where they have used nanoparticle was synthesized, then it was loaded into polyvinylidene fluoride. So that was used as a type of work, but its efficiency and the characteristics, everything, it will be different, because whatever the material they have used, so that is different. So coming to the battery application, so here also we can make use this technology that is can be used. So we all know that this lithium ion battery is it is used everywhere, correct? Now if you look at the different components of we have cathode, we have electrolyte, and we have separator, correct? No, so the charging and discharging phenomena of lithium ion simple. So it is just a movement of lithium ions between cathode and anode, correct? No, so during charging and migrate from anode to cathode. So here, whatever the separator we use here, so that has very play. So that has to be proper, and if it is not proper, the transport of lithium ions during charging and discharging, it cannot be that effective. So decides the efficiency of the battery, correct? No, so here the commercial polypropylene, but this certain disadvantages at times. What happens, there will be some thermal shrinkage or even melting phenomena could be at high operating. So and thermal runaway of the lithium ion batteries. To avoid that, see, one can see here, anode also can be modified, cathode also can be modified. Clear? So anode surface of the anode can be modified with the surface of the anodic material should be coated by using electrospinning technique, so that you will have large surface area doping, effective doping of lithium ions during charging and discharging, correct? So that you can increase the efficiency of, and also can be modified. And at the same time, the electrolyte, you can play with electrolyte also. And electrolyte can also be modified with the the PVP was dissolved in isopropanol, and titanium isopropoxide was added, and then that was used as a and that showed efficiency. See, this is a different some image have shown. See how the morphology of the nanofiber mat will change once you dope with the inorganic. See here, it is like very smooth and very clean. Once you dope with the titanium dioxide or silica, any other inorganic substance, changed completely, correct? So here we have porous structure. So it is always fascinating that once you additives to the nanofiber in polymer solution, if you elect properties of the nanofiber you have received, so that completely, so its properties, I mean efficiency and its applications. So again, this can also be used in the substance from the wastewater, correct? So we all in day-to-day life we come across organic pollutants. They're very difficult to uh, we have to go for some advanced technique to clean in the correct, no? So because dealing with certain organic impurities, it is extremely difficult. So this by using electrospun nanomaterials, so the surface of the nanofiber materials could be modified so that can or can have the affinity towards certain toxicants, which can gradually it can absorb the impurities and can be subsequently that can be removed from the wastewater. And this is one strategy that was published. And here they have taken cyclodextrin they have taken, and then it was mixed with 1 2 3 4 butane tetracarboxylic acid, and then it was subjected. So once you get the nanofiber mat here, then it was subjected for heat treatment to an insoluble poly-CD nanofibrous membrane. Okay, so this the membrane was full of several impurities, heavy metals also. It was found that even could be effective in the removal of heavy metals like lead, copper also could be. See, this is another nanofiber mat to remove the oil, the water. Okay, see here, whatever we can see in the image, that is in red color, right? So that is color. It is colored oil. Just for our identification, the oil, whatever is there here, so that is colored. Clear? See, this is a fabric. Put it on the surface of this oil. So this has the ability to absorb absorb only the oil, not the water. So such type of nanofiber mat also could be fabricated. Here, whatever the mat we have, so that was fabricated by taking beeswax and polycaprolactam. Yeah, and oils of some oil sock capacity 16.95 to 31.05 gram per gram in different oils. The fabricated nanofiber mat was a little different, but it was more efficient than the previous work. So where the contact angle was degree, and it had the ability of it could absorb for silicon oil. So coming to the last application, so that is application of electrospun as an emissive layer in OLED. So when it comes to LED application, we all know even OLED has different components. Like we have cathode, anode, we have hole transporting material, and we have electron transporting material. In the middle, we have emissive layer. Correct? No, the role of emissive layer is very important. So we have OLED, we have so many organic compounds, organic molecules we have, so which can the energy and can be excited to higher energy state. While coming back, absorbed energy will be liberated in the form of light that can be seen colors. So that main agenda behind this OLED is to achieve white light. Correct? No? So here also, say as a cathode, we have here also we have more scope for the modification with this electrospun nanotechnology. But for today, I'll be related with the emissive layer. How emissive layer could be modified using electrospinning technique. Clear? So here, so this work was published in Journal of Molecular Structure. So here was of a polymer, and two different dopants were used. So these two were the derivatives of 3-hydroxy. Two different molecules have taken, and so this was the nanofiber mat. See, from the nanofiber mat, it was found. I mean, one see that the difference fiber morphology. So as the fiber morphology increased, the size of the nanofiber the found to be reduced. So that is mainly due improvement in the crystalline nature of the nanofiber. See that whatever dopant was highly crystalline, but upon incorporating in the nanofiber mat, since the crystalline in nature, I mean semi-crystalline in nature. So the resultant nanofiber mat also, it was little bit semi-crystalline. It was not completely crystalline. Okay, so here, so this is a dopant one where the fluoro derivative of 3-hydroxyflavus. But the morphology was completely, so it was, the fiber was not continuous, it was cut in between. Okay, so that is how once you add the dopant, a nanofiber mat, it will be varied completely, it will be changed. And again, to understand pullulan and dopant, the FTIR was used. So here FTIR, from FTIR, one could see that the, see, for whatever the fluorine containing dopant, it was found that interact pullulan backbone through hydrogen linkage. That is why there was a there is a shifting of OH band on this group, is hydroxy group, whatever is there in the molecule, that was shifted towards lower wave number. So in case of see percent dopant, it was shifted to 3287 from 3317. So that is mainly due to the interaction of the dopant polymer or with the microenvironment. And this is UV visible spectroscopy, I told, to be used as a emissive material. One has to go with the UV visible spectroscopy. See, from for the molecule showing two peaks. Okay, so the dope absorption 248 nanometer, and the absorption pattern of the dopant molecule did not change in the fabricated mat. See, after incorporating in the nanofiber mat, the UV band did not change. That is because here in this case, in this dopant, so there was not there much interaction between the dopant and the polymers. But in case of this fluorine containing dopant, so one could see the first band was shifted. So initially it was at 2 nanometer for the fabric nano. So the one could see the bathycrylic shift, that band higher, that is the interaction, that is that could be mainly due to the hydrogen bonding interaction fluorine atom. So because fluorine is highly electronegative, that has the ability to interact with the, has more ability to interact with the more chances, we can say, to interact with the nanofiber mat. And to see, whenever we, it has a emissive layer here, it is very important to study the fluorescence properties, correct? No, so you fluorescent properties, at times what happens is, once you dope the compound in the nanofiber mat, say before doping it may be fluorescent, or after incorporating in the nanofiber mat, it cannot it may not be that fluorescent. So it is very important study the fluorescence property of the fabricated nanofiber mat. So generally, crystal structure, the understanding its crystal structure is very important. That can ultimately it will decide the of the nanofiber mat. See, in this, whatever derivative was there, so it was almost it was having its structure in its it is a single crystal image here. See, this is OTEP weave and crystal pack. So if you look at the crystal packing here, it is not a plain structure. So because of the presence of dimethoxy group, so these that phenyl group, whatever was there, so that cannot lie in the same plane. So it was motion angle and oxygen. This it found 1.7 twisted orientation. Plus side another whatever was there, and here also, so this one could see it is found that it was anticipated to show J aggregation. So we have to to understand emissive property of the proper emissive behavior of the fabricated nanofiber mat, one has to understand the crystal packing of the molecule properly. We have different types. See, molecule inside the nanofiber mat, the molecule can take up different variations. So can orient in a aggregation for pattern or J aggregation or X aggregation. So see, from the fluorescence studies, it was found that see the dopant was dual emissive, and so in case of so the emissive profile of the nanofiber mat, it was similar to the dopant. So there was no change in, so that was mainly due to the X aggregation of the molecule, because since the compound was twisted in its crystal, it retained its original emission profile. So, but in another this fluoroderivative, it was showing slippage angle of around 36 degree. So because of that, it could show J aggregation of that. See the peak, whatever was there. See for dope, the first peak was at 4 nanometer, fat nanofiber mat. So it was 460 nanometer. So it was not same as the dopant. So the bathochromic shift of 26 nanometer, that could be mainly due to the J aggregation. So this will be dual emissive, that is mainly to the S, that is intramolecular proton transfer mechanism. Actually, we can encounter here, so that we can see dual emissive property. So it is very important once we going for emissive application. So it is very important to know the dopant molecule to understand the crystal structure of the emissive crystal structure of, so you can precisely you can say, you can anticipate the behavior of this molecule inside the nanofiber mat. So coming to the end, so far we had discussed about the nanomaterial and its, and then later we had discussed about several applications, application as a drug delivery mat, and then a wound as see that is dye-sensitized solar cell battery application we discussed, and removal of toxicants from water, and had discussed OLED application of this nanofiber mat. So these are certain challenges and the limitations that we come across. So the scalability. So scaling up production for industrial application remains a challenge. In some cases, it will be difficult. So sometimes we cannot go for higher flow rate. So you see, imagine if you keep the flow rate very less, so you take a lot of time to get a desired thickness of the nanofiber mat, and also it remains a challenge. And uniformity, maintaining a consistent fiber diameter, so that is also here a challenge. See, once you want to go technique with the same voltage and with the same solution properties, the morphology may not be exactly same as the previous one. So since solutions stable factor, so the getting the consistent fiber is bit challenging here. So reducing the for widespread commercialization, again it is a challenging, and safety and environmental impact. Ensuring the and environmental compatibility of the material major concern. And suppose if you are using some synthetic material for the electrospinning technique, and it has to be addressed properly. And even if you are using it as a biomedical, if you are using it for the so the toxicity of this nanofiber mat has to be addressed properly, and it is still a challenge to the proper toxicity of the nanofiber mat, as we are dealing with extremely extremely small material. And coming to the conclusion, spinning is one of the most efficient techniques used for the synthesis of nanomaterials. So it imparts unique properties to the nanofiber of various interest, correct? So we can add different types of dopants, and we so different polymers we have different options when it comes to polymer, or it can be a dopant, or it can be a polymer. We have, luxury of options, correct, no? So for this, and even though the literature on electrospun nanofibers are plenty, much space is still explore the novel application in fields such as agriculture, formulation, and food packaging. So we have so much of scope for this subject, where we can explore this material in different fields. Thank you.
Thank you so much, Professor Dayananda sir, for such an enlightening and inspiring session. Your deep insights, clear explanations, and passionate presentation have truly left us with much to think about and explore. We deeply appreciate your time, effort, and dedication in sharing your valuable knowledge with us. It was indeed a privilege to learn from you. Now, the session is open for the discussion. Participants can unmute and ask their queries. Participants, if you have any doubt or if you want any clarification, you can unmute yourself and ask the question from Dayananda sir.
So I have provided my email ID. If anybody to have if you have any doubt regarding the topic, you can read at any time.
Dr. Ansuya, madam, you can unmute and you can ask your question. Dr. Ansuya, ma'am, can you?
Yeah, I can see the questions from the message. uh, Dr. Smita MG had raised a question that can this electrospun technique be used for solar cell application? Yeah, even in solar application also have, scope for this technique. So you can modify the, even in solar cell, we have cathode, more amount more light, we can modify the uh, you know uh, base material, electrospun nanomaterial, but we have to make sure that whatever the we are gonna load in this towards, I mean, that is stable towards solar energy, I mean energy. So that we have to, that is what I had explained. Like in die-size solar cell, also we can use. Even in also this can be applied.
Participants, those who cannot unmute yourself, you can message there your question. Sir is waiting for to answer your questions. You can message in the chat box.
Uh, so what about the submitted molecules in synthesis? Uh, yes, ma'am. See, I have used certain, cyclic molecule, heterocyclic compounds. I have used that I have loaded in the electrospun nanofiber mat. See, whenever we synthesize, if it is even if it is a heterocyclic compound, so ultimately it'll go for biomedical application, either anti or anti-cancer, antioxidant properties. Correct, no? So to be used as a effective wound dressing material, or to deliver from the wound dressing, so we have to optimize the condition before it. So we have to do that, we have to load the compound in the nanofiber mat, and then we have to study its drip. And along with whatever nanofiber mat can also be used as a patch for antibacterial application. That also can be, see, once you fabricate the nanofiber mat, so that later you can dissolve that, and you can also check anti-inflammatory property also. And see, even in also you can check it. So if you want to use it for fluorescent applications, if you synthesize heterocyclic compounds, so that create particular type of polymer, and its photophysical properties also could be studied.
Any other question? Participants can unmute and you can ask your questions. Or else, if you can't unmute, you can message your questions on the chat box.
uh, so whatever the research work I have explained here, all are not my research work. So mine was like drug delivery application I had explained in the beginning. There I had used 3-hydroxyflavone derivative, and at the end uh, used for fabrication of fluorescent material. So that I have synthesized. So that was I have synthesized in the laboratory, and that I have used. After I have taken So taken from the Sci-Hub and that I have explained field.
Thank you, sir, for answering the questions raised by the participants. So by this, we come to the end of today's FDP. Participants make a note, feedback link that is shared in the WhatsApp group. Tomorrow's session subject is physics and the topic is unmasking the physics around us. Will start sharp at 10 a.m. morning. A request all the participants to join with the shared link. Thank you one and all and have a great day ahead. See you.
Ma'am, we have one more question here. What are the methods can be used to solidify solution? See this. See whatever. If you have the solution form of nanomaterials, that can be, optimized for see it whether we can spray by using this electrospinning technique. So that is well and good. So in this electrospinning technique, initially we polymer solution and then we spray it. See, after spraying, once it reaches the collector, so you will get the solid form of nanomaterial itself. So if solvent is in most of the cases, solvent will dry during the travel towards collector. So suppose if you have a solution where you have that, if it is electrospinning, and you will end up with the uh, you know solid material, so that will be having your nanoparticles in that.
Okay, I hope the questions have ended here. So thank you one and all. We see you tomorrow. Have a great day ahead. Thank you, sir.